Hello students, today's session we begin by discussing the properties of an electric cell. So we shall discuss what are the properties of a cell. So you know that a cell is a device which converts chemical energy into electrical energy. So every cell converts chemical energy into electrical energy, and there are certain terms associated with the cell, and the first one is EMF. EMF of a cell is actually the terminal potential difference of the cell when the cell is in the open circuit. So this is the symbolic representation of a cell. This line represents the positive terminal, and the other one, the shorter one, represents the negative terminal. So the first one is the EMF of a cell, which I told you is the terminal potential difference of the cell when the cell is in the open circuit. That means open circuit means cell is not sending any current. So that is EMF. Now next one is of course the terminal potential difference, terminal PD. Terminal potential difference, which is the potential difference between the two terminals of the cell when the cell is sending a current. Now we know that a cell sends a current at a constant voltage. The voltage across the terminals of the cell remains constant when it is working, but the current is not a constant. Now what is the another point regarding a cell is a term called internal resistance. So the third one is internal resistance. Internal resistance is the resistance offered by the medium inside the cell, which we call electrolyte, to the flow of electricity through it. So the resistance offered by the medium, which is electrolyte inside the cell, to the flow of electricity through it is called internal resistance. So the first one is EMF, second one is terminal potential difference, and third one is internal resistance. And the relation connecting these three is V equal to E minus IR. So when we take a cell and connect it across a resistor, or rather we take a resistor or any conductor and connect it across a cell, the cell begins to discharge through that conductor, and then the terminal PD EMF relationship is given by V equal to E minus IR. Now as I told you earlier, EMF is the terminal PD when the cell is not sending a current. So in this equation, if you put I equal to 0, you will get V equal to E, or rather E equal to V. That is the relationship between EMF and terminal potential difference. So when the cell is not sending a current, you see that E equal to V. Now we can also define EMF in another way. EMF is the cause of potential difference. You know that according to Ohm's law, if a current flows between any 2 points across any 2 points in a circuit, certainly a potential difference has been developed across those 2 points. So in order to maintain a constant potential difference across any 2 points in a cell, a source of EMF should be connected, and that source of EMF is normally what we call cell or group of cells named as battery. So what happens is, if there is no source of EMF, there will be no potential difference. So that is why we say that EMF is the cause of potential difference. So those are the terms, those are the explanation of the terms EMF, terminal potential difference, internal resistance, and generally what is meant by a cell. Clear? Now let us see some of the factors upon which this internal resistance depend. So the internal resistance of a cell depends upon the distance between the electrodes, distance between the two electrodes, then the nature and the area of the electrodes, the nature and area of the electrodes, and finally the medium between the electrodes, which is called the electrolyte, its concentration, the concentration of the electrolyte. So these are some of the factors upon which the internal resistance of a cell depend. Distance between the electrodes, nature and area of the electrodes, and the concentration or the nature of the medium between the electrodes, which we call electrolyte. Okay. Next we shall discuss the combination of cells. First we will discuss combination of cells. Combination of cells. So first we will discuss the series combination of cells. Series. Suppose we have n identical cells, each of EM of E and internal resistance R are connected in series across a resistor of value R. So we have n identical cells, each of EM of E, internal resistance R, connected to an external resistance capital R. Then we will write the expression for the current drawn from this combination. The current is given by I equal to, each cell has an EM of E and n such cells are in series, so the net EM of is NE. Similarly, the net internal resistance in series is NR and the external resistance is capital R. So this is the current drawn from the combination. I equal to NE by NR plus R. Suppose NR is much smaller than capital R, then the current will be N into E by R. So if the internal resistance is much less than the external resistance, then the current will be N into E by R. So in the case when the internal resistance is much less than the external resistance, this type of combination is preferred, series combination of cells. So the expression for the current is NE by NR plus R when you connect cells in series and aiding. These cells are aiding each other. You know that the SL sends current. How do you define SL? That is, how do you identify a cell that is discharging and another one that is being charged? See, when we have a cell connected like this, look at this one. This one is a discharging cell. Why? Because the current leaves from the positive terminal and enters through the negative terminal. That is the sign of cell that is being discharged. And for this cell, we have the equation V equal to E minus IR. Now, suppose you have another cell which is in which the direction of the current flow is like this. Then the current is entering through the positive and leaving from the negative. This is a charging cell and the terminal PD will be more than the EMF. Generally, the terminal PD of a cell is less than the EMF because most of the time the cells are being discharged. But you know that there are many rechargeable cells like the one in your mobile phone, then the inverter in your house. So all these type of cells are rechargeable cells. So when a cell is being charged, the terminal PD will be greater than the EMF. So this is the only situation when the terminal PD becomes greater than the EMF of the cell. So these cells were connected in series and aiding. Current is leaving from the positive and entering through the negative of the other cell. So when cells are connected in series and aiding, the current will be NE by NR plus R. Now we connect the cells in parallel. The second one is parallel combination of cells. Again we have n identical cells, each of EM of E and internal resistance R connected across a resistor. So there are n such cells here which are all in parallel. So we now connect them across a resistor of capital R. So this has an EMF E internal resistance R. The other one also has the same EMF E internal resistance R. All the n cells are connected in parallel. Between the 2 points A and B are identical, and this is the external resistance R. Now let us write down the expression for the current drawn from this combination. You know that in parallel combination the voltage remains constant. So EMF of a single cell is E means the EMF of the combination is also E. So net EMF is E divided by, in parallel combination of identical resistances, we know that the net or rather effective resistance is R by N. So R by N. The internal resistance and external resistance appears in series, therefore this is plus R. So this is the expression for the current in the parallel combination of cells, I equal to E by R by N plus R. Now in the case R much less than small r, external resistance much smaller than internal resistance, we will write the expression for the current as I equal to N into E by R. So when the external resistance is much smaller, then the expression for the current will be I equal to N into E by R. So this type of combination is preferred when the external resistance is much smaller than the internal resistance. Now there is a third type of combination called a mixed grouping or series parallel combination of the cells. So we take, that is our third point of discussion, mixed grouping of cells. Mixed grouping of cells. Mixed grouping, or it's also called, known by the name series parallel combination. So as the name suggests, there are n identical cells, each of M of E and internal resistance are connected as M rows. In each row we have n cells, identical cells, and there are such M rows in parallel, and the combination is connected across a external resistance, across an external resistance capital R. So this is our external resistance. All the cells are identical. So there are n such cells in a single row, and as I told you, there are m such rows in parallel. So this is external resistance R. Now what is the current drawn from such a combination? The EMF of a single cell is E, the EMF of n cells in series is Ne, and whatever be the number of such cells in parallel, the EMF remains constant. So EMF of the combination is Ne. Now divided by, in parallel combination the effective resistance, in series combination the effective resistance will be Nr. M such rows are there in parallel, so the effective internal resistance will be Nr by M, and the internal resistance comes in series, so Nr by M plus capital R, or we may write it as Mne divided by Nr plus Mr. So this is the expression for current in series parallel combination of cells or mixed grouping of cells. Mne by Nr plus Mr. Now the current will be maximum. The maximum current you will get maximum current I equal to I max when Nr equal to Mr or R equal to Nr divided by M. This is the condition for obtaining maximum current from the mixed grouping of cells. So external resistance should be equal to effective internal resistance. Then this combination will send maximum current through the resistor. Clear? So we have seen the series combination, parallel combination, mixed grouping of cells. Let us see now for what purpose each type of combination is used. We will start with the series combination. For what purpose or what is the use of connecting cells in series? The series combination of cells is used to get maximum voltage. So the series combination of cells is used to obtain maximum voltage. And the next one is parallel combination, and the parallel combination of cells is used to get maximum current. And finally the mixed grouping of cells, that is used for getting maximum power. So this is for getting maximum power. So series combination of cells is used for getting maximum voltage, parallel combination for getting maximum current, and mixed grouping of cells is used for getting maximum power. We now discuss some points about the power delivered by a cell or the power dissipated in an external resistor. And the formula for the power dissipated in an external resistor is P equal to I square R, where I equal to E by R plus R. R is the external resistance. So we have a cell of EM of E, internal resistance R, connected parallel to an external resistance capital R, connected to an external resistance capital R. Now let us see when this power is maximum. Now this is the expression for power. So this will be maximum when dP by dR equal to 0. That is when you differentiate this term. So I equal to E by R plus R. So P is equal to E by R plus R the whole square into R. We have to differentiate this with respect to R and put it equal to 0. then we will get a condition that small r equal to, or rather capital R equal to small r. So when the external resistance and internal resistance become equal, the power delivered by the cell will be to the external resistance will be maximum. This is called a maximum power transfer theorem. So the maximum power transfer occurs when the external resistance and the internal resistance become equal. Now at that time, what will be the current? We will see what the value of the current is when the maximum power transfer is taking place. E equal to E by R plus R, capital R equal to small r. So the current will be E by 2R. So this is the current when maximum power transfer is taking place. Now when capital R equal to 0, what is the current? Here in this expression, let us put capital R equal to 0. Then the current will be E by small r. This current is called a short circuited current. And what is meant by short circuiting a cell? Short circuiting a cell means establishing a connection where no connection is intended. So if you connect the positive and the negative terminals of a cell directly by using a wire of negligible resistance, then that is short circuiting the cell. So short circuiting means establishing a connection where ordinarily no connection is intended, or connecting with a light load. This capital R is also known as load. So when you make the value of the external resistance, which is called load, equal to 0, or if you connect the load resistor which has a very small value compared to the internal resistance, we say that the cell is being shorted. So when you short a cell, this is the current drawn from it. You know what happens when the cell is shorted? It will deliver a large current can be drawn from such a cell for a very short time, and the cell will be damaged due to overheating. So that is what is meant by short circuiting the cell. So when you short the cell, the current will be E by small r. But when maximum power transfer is taking place, the current is E by 2R. So we can say that the max current that flows when maximum power transfer is taking place is only half of the short circuited current. Short circuited current is E by R, and the current at maximum power transfer is E by 2R. So this is only half of this. But that is a steady and sustainable current. So when a question is asked like this, what is the maximum current that you can get from a cell, then the answer should be E by 2R, not E by R, because even though E by R is much greater than E by 2R, this is not a sustainable current because the cell will be damaged due to overheating. But this current is sustainable, and this is the maximum current that is flowing when the maximum power this is the current that is flowing when maximum power transfer is taking place. So that is the difference between these two currents. Let us discuss two important laws in an electric circuit called Kirchhoffs laws. Kirchhoffs laws. So Kirchhoffs laws in an electrical circuit is very helpful for us in determining the current and voltages at different parts of an electric circuit. So let us look at them in brief. I have already made a video explaining in detail how Kirchhoffs laws can be applied to a circuit. You can find them in my channel. So the first one is known as Kirchhoffs current law or junction rule. This is also known as junction rule. So Kirchhoffs current law is also known as junction rule, and this law is based on the conservation of charge. So the law says that the algebraic sum of the currents meeting at a junction is equal to 0. So you know that a junction is a place where more than two branches meet. In an electrical circuit, if you have a branch, suppose this is a branch this is a junction where there are 3 or 4 branches through which the current arrive or leave. So this is one branch through which a current I1 arrive, then this is another one I2, through this one a current I3 is leaving, through this for a current I4 is leaving, and through this one current I5 is coming. So this is our junction node. So if you try to apply Kirchhoffs first law, which is the junction rule here, we have to assume that the incoming currents are given a positive sign and outgoing currents are given a negative sign. So and what we will write is I1 plus I2 minus I3 minus I4 plus I5 equal to 0. Or we may write I1 plus I2 plus I5 equal to I3 plus I4. This is also known as the sum of the currents arriving at the junction equal to sum of the currents leaving the junction. So that is Kirchhoffs current law, which is also known as junction rule, and it is based on the conservation of charge. The second law is known as the Kirchhoffs voltage law or loop rule, KVL or loop rule. And this law says that in a closed network of conductors or in a loop, the algebraic sum of the product of current and resistance of each branch is equal to the net EMF of the loop. So what is meant by this statement? I will explain. Suppose you have a closed network like this. You have a cell and there are 2 or 3 resistors like this, and let this be E, or this one is R1, this is R2, this is R3, and this is R4. So your current flowing is flowing in this direction. So what this law says is that in this closed loop, the algebraic sum of the product of current and resistance of each loop is equal to the net EMF of the loop. So this law, while writing in the mathematical form, some certain sign conventions are to be followed. And what are the sign conventions to be followed? I shall explain. So you take a resistor and the current is flowing through this resistor in this direction. So when you are traveling through a resistor, if you are traveling in the same direction as that of the current flow, the product of current and resistance should be considered as negative. So here I am traveling in the same direction as that of the current flow. Let me travel from A to B. So when I walk through this resistor from A to B, I am walking in the same direction as that of the current flow. Then the product of current and resistance should be negative, minus IR. That also means that I am walking in the direction of decreasing potential. Current always travel from higher to lower potential. So I am traveling in the direction of the decreasing potential. So there is a decrease or drop in potential which is represented by minus IR. Now what if I was traveling in the opposite direction from B to A, then I was traveling in the direction of increasing potential. So that will be represented by another symbol, plus IR. So if you are imagine that you are walking through a resistor. You are walking in the same direction as that of the current flow. Then the product of current and resistance is negative because you are traveling in a direction of decreasing potential. If you are traveling in the opposite direction of the current flow through a resistor, the product of current and resistance should be positive because you are traveling in a direction of the increasing potential. Now what about walking through a cell? When you are walking through a cell, you know that a cell has 2 terminals. The positive terminal is the one with a higher potential and the negative one is a terminal with a lower potential. So while walking through a cell, if you are walking from the positive terminal to the negative terminal of the cell, you are again traveling in the direction of the decreasing potential. So the EMF of the cell will be negative. While if you travel from negative terminal to positive terminal, you are traveling in the direction of the increasing potential. So the EMF of the cell will be given a positive sign plus C. So while applying all these laws here, or while following all these sign conventions here, we can write minus IR4 minus IR3. So let me write it as here, minus IR4 minus IR3 minus IR2 minus IR1. Now I travel through the cell in the direction of the increasing potential, plus E equal to 0. That is how we apply the sign convention and the Kirchhoffs loop rule to this loop. Clear? So follow these sign conventions very closely. If you follow these sign conventions or follow the rules that I have just now given, you will never commit a mistake while solving a circuit using Kirchhoffs second rule. Okay.